Alright everybody, welcome back to another video. I'm going to be taking you through this example where we're going to be talking about double integrals using polar coordinates instead of rectangles. Okay, so the first thing with this question is we should probably graph it. So let's get a little graph going. Here are our axes. And basically this is parabolic in the x and the y directions, so it's kind of going to look like that, like that, and then kind of like that, and like that. Actually, we can do better than that. So this is kind of what it looks like, and I can kind of make it even clearer if I draw another line kind of there. But basically the profile of this in the XY plane is a circle. So this D, this region, basically looks like this. So we have So this is basically what it looks like. It's a circle of radius 4. So this is our D. And you can see that actually this is either type 1 or type 2. Okay? This is both. And I'm going to make a video on what that means, but essentially you can integrate both ways because you can draw both a horizontal and vertical and it goes straight through. But I will do a video on that, maybe tomorrow or something. Okay, so we've got this region, which is a circle. And as I said, you can, well, it's type 1 or type 2, which means we can do this using just, you know, the method we used previously in the last video. Just imagining there's a kind of a rectangle around it. And that would kind of look like this. So in rectangular form, your double integral would kind of be, if we're treating this as a type 1 region, we'd be going from -4 to 4 on the outer integral, and we'd be going from root 16 minus x squared to, sorry, from minus root 16 minus x squared to positive root 16 minus x squared. And that's because this, right, this circle here has the equation 16 minus x squared minus y squared equals 0. So if you rearrange for y, this is what you're going to get, okay? However, I don't think that this form is ideal for this because we have this root here, which makes evaluating it pretty difficult. So this is actually pretty well suited for using polar coordinates. I'm just going to write down, let's use polar instead. And that will involve us having to rewrite this equation in terms of polar coordinates, okay? So let's just rewrite this equation. So it's f of xy equals 16 minus x squared minus y squared, okay? So that's the equation. And if we want to basically make that, we want to turn that to polar. So, okay, remember that when we are going from Cartesian coordinates to polar coordinates, we need to use this formula, x squared plus y squared equals r squared. And we see we have this minus x squared minus y squared, which equals minus r squared. So this can be rewritten as 16 minus r squared. And we're going to rewrite that in polar, so it's going to be, that should look like, so, yeah, this is going to be our, let's just get rid of that. This is going to be our equation in polar coordinates, okay? Pretty simple, right? And this looks a lot easier, right? Because now, when we set up the integral, what we're going to have is, so we're going to go from 0, okay? We're going to go from 0 to 2 pi, because that will trace a full circle. And we are going to go from 0 to 4 on the, what's going on? And we're going to go from 0 to 4 on the inner integral, because that is, if we imagine, sorry, let me just get rid of these green markings. If we look at this circle in polar, we have this concentric circle where r equals 4, and then, you know, we can imagine the origin r equals just 0. So it's going from 0 to 4. And our equation of the actual line is 16 minus r squared. And then we need to add the area element. So the dA, all double integrals need that dA. And in polar, that is r dr d theta. So that is the same as dA in polar. And so now we can actually go ahead and just compute this. So let's first just let's expand out the bracket. So we got 16r minus r cubed from 0 to 4. Let's also separate this integral. So the d theta is going with this integral here. So we can say it's from 0 to 2 pi times d theta dr. So what we have there is, we can imagine like there's basically like a 1 here. So that's just going to be theta. So it's going to be 2 pi. And then in brackets, here we got, let's just integrate 16r minus r cubed. We're going to get 8r squared. 8r squared minus 3r, sorry, what am I doing? A quarter r to the 4, and that's going from 0 to 4, so that equals, what do we get? We get 16 times 8. All right, let's do that mental math. 80 plus 48 is 128. So 128 minus 4 to the power of 4, well, over 4, so it's 4 cubed minus 64, which is multiplied by 2 pi. So what we get is simply 64 times 2 pi, which is 128 pi, and that is our final answer.